Let's consider a piping system that looks like this. We've got a tank, a closed tank, which has water in it, and air up above that water pressurized to 10 bar, so 10 atmospheres. And because that gas is compressible, that will continue to exert some downward pressure here to drive the flow through this piping and over to this tank over here. Now this is a made-up problem, but it allows us to exercise all of our efforts in calculation. Water flowing through the pipe. There are elbows, 45-degree elbows. There's a gate valve here and a globe valve over here. And the pipe comes down into this reservoir here and then discharges through an exit. So we've got a sharp entry here, an exit over here, and fittings in between. And we've got an elevation difference driving the flow, 15 meters elevation difference, and a 10 bar pressure difference driving the flow. So both of those are pushing the flow through this piping system. If we're told that it's a 3-inch pipe and it's been installed for a while and it's rusty, Schedule 40 welded. So welded pipe will be about the same as flanged pipe for the fittings, fairly smooth on the inside. And that the total pipe length is 50 meters. So 50 meters along that path there. We'd like to know what is the flow rate that goes through that pipe from over here to over here. Now from the web I find that a 3-inch Schedule 40 pipe is 3.5 inches outside diameter with 0.216-inch wall thickness. So that's just a little bit over 3 inches or 78 millimeters inside diameter. If I go to my textbook, in this case I was using White, which is another textbook like Munson, I find a roughness of about 2 millimeters for old rusty steel pipe. So I can calculate the relative roughness as 0.026. This is quite a rough pipe. I've got one sharp entry, so the K factor for a sharp entry is about 0.5. From the table, a gate valve has a K factor of 0.25. Fairly low because when we back the gate right out of the way, the pipe's fairly open. 3 90-degree elbows from the table, they're 0.35 each, times 3 of them is 1.05. 2 45-degree elbows, so about 0.2 times 2 is 0.4. A globe valve. The table in White says 7.3 for a globe valve. That's quite a high loss coefficient. And then the exit, of course, 1.00. So the dominant effect here is probably going to come from this globe valve. And if we sum up all those losses, the sum of all the loss coefficients is 10.5. Now we'll look here. We can make that location 1 at the surface here where we actually know the pressure is 10 bar and the fluid's hardly moving. We're picking that location because it's easy to put into our Bernoulli equation. Over here at the other end, following a streamline all the way along, we'll pick this location too, again because it's easy. We know that the pressure is atmospheric, we know that the velocity is about 0. So we write Bernoulli's equation for both the point 1 and point 2, and the energy we'll have left at point 2 will be what we had at point 1, but we've lost the head loss due to friction and the minor losses along the way. So we wind up with the difference in the two heights driving the flow, the difference in pressure driving the flow, equal to FL over D, V squared over 2G, that's delta HF, and sigma K, V squared over 2G, that's delta HM. Rearranging that, we can get the velocity in terms of the square root of all of these things together. We know sigma K, we don't really know F yet, because F is going to be a function of the Reynolds number and the relative roughness. So we're going to need to guess F along the way. If we plug in some numbers there for everything that we know, we can simplify things down a little bit. So the velocity will be equal to 2 times g times the other values here all plugged in to match up with the equation we had before. So if we look at what we had before, 2g h1 minus h2 of 15 meters plus p 10 times 10 to the 5, 10 bar over rho g. All divided by 50, the length of the piping, over the diameter, 0.078 times f, plus the sum of the loss coefficients, 10.5. Plugging the numbers in, I get 47.9 over the square root of 641f plus 10.5. So if I guess that f is 0.02, always a good first guess, that'll give me a value of v equal to 9.92 meters per second. Calculate a Reynolds number on the basis of that velocity, and I get 7.7 times 10 to the 5th. The relative roughness, I know from the roughness value I got before, is 0.026. When I go to the Moody diagram, I find that f is equal to 0.053, way different than the 0.02 that I guessed. So this velocity is going to be quite wrong. When I go and repeat the calculation, my new guess for the friction factor is 0.053. That gives me a velocity of 7.18 meters per second, a Reynolds number of 5.6 times 10 to the 5th. And when I check Moody again, I get a friction factor of 0.053. So I've converged quickly, even when the f was not even remotely close to 0.02. So I find the velocity ought to be about 7.18 meters per second, plus or minus about 15%. And the flow that I'll get is the velocity times the area, or velocity times pi d squared over 4, and that will be 0.0343 cubic meters per second. Now expressed that way, that doesn't sound like very much, but remember, 1 cubic meter is 1,000 liters. So this is actually 34.3 liters per second, or about 34 kilograms per second. That's quite a lot of water coming through that line.